These are the spiders in the cold.
Hello YouTube. Obviously, I get asked a lot of questions about spiders. I get asked other questions too, like, why are you like this? And would you like the protection plan with that? But there are certain spider-related questions that come up again and again, and this is one of them. What happens to spiders in the winter? If you live in Florida, you may not have thought about this a lot, until this year's polar vortex hit you. But at higher latitudes, temperatures during the winter months drop below freezing, sometimes way below freezing. Despite this, somehow, spiders always reappear in the spring, despite the fact that many of them aren't much bigger than a drop of water and look like they would freeze solid in seconds. How do they do this? Do they migrate south like birds and come back when the snow goes away? Do they burrow deep underground somewhere and hibernate like bears? Do they all just come inside and hope you don't notice them for a few months? Do they just freeze to death and somehow a new population of spiders shows up from the tropics every year? Turns out, spiders have a few adaptations when it comes to not freezing to death every year. Different spiders do it differently, and they don't care how you feel about it. They use a combination of behaviors and adaptations to survive some pretty harsh conditions, which I guess they find preferable to just giving up and dying once Halloween is over. I'll dive into all of that in this video, but first a very quick thank you to Dr. Catherine Scott and Dr. Sean McCann for their assistance with the research on this, and to my wife for suggesting a ton of revisions and edits to the script for this video that ultimately made it somewhat coherent. Thank you. So, what are the secrets to how spiders survive the winter? Let's start with the actual nature of the challenge. Spiders are ectotherms, meaning they don't produce their own body heat. It's regulated largely by the temperature of the environment. So, surviving the winter means finding a way to not freeze solid when the temperature drops below freezing. That brings along a couple of other challenges. Even if they can avoid freezing solid, the lowered temperature slows their metabolism to a point that prevents much activity or movement. Meaning two things. First, they're less able to catch prey, and second, they're less able to defend against or flee from predators. This is kind of like trying to find a place in downtown Toronto to take a week-long nap and wake up with your wallet still in your pocket. The obvious question then is, where do they go? As humans, we tend to just avoid cold altogether and find other things to do. There's a reason all those photos of pristine snow have no people in them, and a reason so many birthdays are in September. Some spiders aren't much different from us in that regard. Cellar spiders, for instance, have become so accustomed to living alongside humans that they mostly spend the winters indoors. Our friend the giant house spider, Eratogena atrica, is somewhat famous for showing up in houses when the temperature drops. But just coming inside your house isn't an option for most of the spiders out there, a fact for which many of you are eternally grateful. So most need to find a suitable hiding place out there in the great outdoors, and most of them move downward. Not quite underground, but close, in the leaf litter or the ground vegetation layer, or under rocks or logs, right on the ground. The litter layer is such a complex environment that it provides lots of places to hide. Think McDonald's play place that covers 100 acres. And with most other invertebrates doing more or less the same thing as the spiders, there's not a ton of activity going on down there. Back in 1977, Matthias Schaefer found that over 80% of all the spider species he checked on in northern Germany spent the winter down in this layer, so this is a real popular choice. Some, like jumping spiders and ground spiders, make a silk sack in hollow plants or under loose bark and snuggle up in that. Some, like certain long-jawed orb weavers, actually spend the winter unsheltered in the upper vegetation layer. A few species overwinter on the outside walls of buildings, like the common house spider. And importantly, many species build their egg sacs in the fall, meaning the eggs survive the winter somehow and hatch in the spring. So we can find spiders in a few places, though it turns out it's not that easy. I tried. What are the conditions in those places? How different are they from the conditions out in the exposed outdoors? There's a reason most spiders spend the winter down in the leaf litter. It turns out the conditions there are wildly different than those above the snow. First and most obviously, they're protected from wind. Second, they're protected from any predators on the surface, like winter-active birds. But perhaps most importantly, it's warmer. How much warmer could it possibly be, you say? Well, I checked. I took one of those wireless temperature and humidity sensors and I stuck it down there in the leaf litter in my backyard, which was under a layer of snow. And I'm not even sure I really covered it back up as well as it was originally. I let it sit there overnight, then I compared the reading it was giving me with the temperature readings from my home weather station, which measures the air temperature above ground. In a rare moment of serendipity, the weather cooperated with me and gave me a nice cold day, showing an air temperature outside of a pretty chilly minus 16.7 degrees Celsius, about 2 degrees Fahrenheit. Normally, I'm not thrilled about cold days, but I was in this case, and so were my kids, who had a snow day. How were things under the leaf litter? They were at a relatively balmy minus 3.4 degrees Celsius, or 26 degrees Fahrenheit. So that's 13.3 degrees Celsius, or 24 degrees Fahrenheit, warmer than the air. That's a big difference. The leaves act as an insulator by trapping air in all the little spaces between them, and that air gets warmed by geothermal energy from the earth, and the snow layer above that acts as a further insulator. No wonder so many spiders and other animals spend the winter there. Loose bark on trees can provide a bit of warmth when the sun hits it, which is why spiders that overwinter under bark are usually found on the south side of the tree, but at night it's not much warmer than the outside air. And conditions in other places spiders might overwinter, like in the upper vegetation layer or the outside walls of buildings, aren't any different than the open air either. Meaning location alone doesn't solve the "I need to not freeze to death" problem. So how do they pull this off? If you just run a Google search on what spiders do in the winter, you'll often be told that they survive the winter by entering a dormant state called diapause. I think I'd go as far as to say that this is outright wrong. Maybe not 100% wrong, as diapause is a thing that happens during winter, but we can find explanations that are not nearly as wrong. And we should, because in spiders, as in life, less wronger is more better. But to understand why this AI-generated answer isn't really right, we first need to understand what diapause is. So, first, it's not necessarily a dormant state. Diapause in spiders is a state in which their further development is delayed, while their metabolism is simultaneously slowed, but it's not like hibernation. There are different kinds of diapause depending on the species, and timelines are helpful here. This line will represent photoperiod, how long the sun is up for each day. Some species mature and mate in the spring, here, and hatch in early summer. They're not supposed to mature until the following spring. So in these species, diapause is triggered by the days getting shorter, and it prolongs the time between molts, slowing down development. This prevents the spiders from maturing, and diapause will last as long as the days are short. So the spiders overwinter as juveniles, and when the days get longer in the spring, diapause shuts off, and their development resumes, and they mature and mate. But some species mature and mate in the fall, and their young are supposed to overwinter in the egg sac. The egg sacs hatch in the spring, and the spiders start growing, but they don't want to mature until here in the fall. If they mature and mate and make egg sacs too early, the eggs may not survive the warmer temperatures of summer, or they may hatch too early and the young may not survive the winter. So in these spiders, longer days actually trigger diapause, again prolonging the time between molts and slowing down their development. And the spiders experience it during the summer. When the days start getting shorter in the fall, diapause shuts off, development speeds up again, and they mature and mate when they're supposed to. Eggs can also go through a kind of diapause. Eggs don't have eyes, so their diapause isn't triggered by light, it's triggered by temperature, which lags behind daylight hours a bit. They might get laid in the fall when it's still warm, and those warm temperatures start diapause almost right away and prevent the eggs from developing until the temperature drops. Then diapause shuts off and the eggs continue their development so that they hatch in the spring, not in the middle of winter. In certain species like hobo spiders, the eggs will never hatch unless they undergo a period of cold temperatures. So diapause isn't actually about a dormant state intended to get the spider through the winter. It's a timing mechanism that ensures the spider hits the correct stage of development at the correct time of year. So while it does slow down the spider in a way, it doesn't have much to do with how they keep from becoming eight-legged chunks of ice. Let's take just a moment to discuss, before we go further, why freezing sucks and usually results in animals not being alive anymore. The problems happen at the cellular level, and the first problem is that ice crystals are pretty sharp. So the crystals can actually puncture and rupture cell walls, which leads to cell death. If enough cells die, so does the animal. Second, there's quite a bit of water between cells in living things, with certain things dissolved in it, and if that water begins to crystallize into ice, all of those dissolved solutes go into the remaining liquid water, causing the concentration of that water to spike. That in turn prompts water inside the cells to migrate out of the cells to balance the concentrations, dehydrating and collapsing the cell. The increased concentrations of solutes within the remaining liquid can become toxic as well. So most animals, including us, can't survive being frozen. I mean, Captain America and maybe Chuck Norris could, but the rest of us would be screwed. There are a handful of insects and other invertebrates that can survive actual freezing, but spiders are not among them. So what adaptations do they have that help them avoid it? A quick note about how I'm going to go about discussing temperatures in this section. All of the temperatures I'm going to say out loud will be in Celsius, unless I specify otherwise. But when I mention specific temperatures, I'll also provide the equivalent in Fahrenheit on screen so that those of you unfamiliar with Celsius will have some frame of reference. If you're listening to this on your way to work, please do not look away from the road to see the equivalents, and just keep in mind that room temperature is about 20 degrees Celsius, water freezes at 0 degrees Celsius, your kitchen freezer is about minus 20 degrees Celsius, and Emperor Palpatine's heart is about minus 40 degrees Celsius. So with that in mind, we move on. As the temperature drops, it will eventually reach a point where the spider enters what's called a chill coma, a point where it no longer responds to tactile stimuli. In other words, you can poke it and it won't do anything. It's essentially a state of reversible paralysis. But this usually occurs somewhere between minus 4 and minus 8 degrees Celsius, below the freezing point of water, and often below the freezing point of the spider's blood itself. And even in this chill coma, the spider might be a long way from death. By the late 1960s, scientists in Germany had documented how certain orb weavers could survive at temperatures down to minus 20 degrees. And we'd seen insects do it too, but we weren't quite sure just how. In 1978, John Duman at the University of Notre Dame in Indiana extracted hemolymph, what we call a spider's blood, from a bunch of running crab spiders that he collected during the winter, then cooled it and warmed it to see what happened. He found that the running crab spider hemolymph froze at minus 5 degrees, but had to be warmed to just above minus 3 degrees before it melted. When the freezing point is different than the melting point, it's called thermal hysteresis, and Duman found that the spiders were producing certain proteins and a kind of sugar alcohol called glycerol that were driving that freezing point a couple of degrees below the melting point. But when he cooled entire live spiders instead of just their hemolymph, they didn't freeze solid until the temperature reached minus 26 degrees, 21 degrees lower than the measured freezing point of the hemolymph on its own, The spiders were doing something called supercooling, which sounds more like something that would happen in a nuclear reactor than in a spider, and yet here we are. Supercooling is what happens when you take a liquid below its freezing point without it actually becoming a solid. You can do this with water. If you have very pure water in a smooth container, you can take it down to around minus 10 degrees Celsius, which is 14 Fahrenheit, without it becoming solid. This is because for ice crystals to form, they need something called a nucleation site, some kind of impurity in the water or a rough surface in the container for water molecules to grab onto to begin the crystallization process. Without either of those, ice crystals won't form, leaving the water in an unstable, supercooled state. If you introduce an impurity, an ice crystal can form on that, or if you shock it, the shock wave can cause enough water molecules to align correctly to start a seed crystal. The moment even a tiny bit of ice crystal exists in the water, a chain reaction causes all of the molecules to align into the crystal structure, and the water flash freezes. This can be a bit tricky, by the way, and it took me a few tries, but eventually I got it to work. Absolutely try this at home, kids. It's a good illustration of how science happens sometimes. We get a result, then we try to duplicate that result, we fail to duplicate it, we try to figure out what was different that time, and that's often what leads us to a deeper understanding of whatever phenomenon we're exploring. There are a bunch of science YouTubers who have demonstrated this supercooled water thing, and even they struggled to get it to work because conditions need to be pretty ideal. Go watch those videos and try it out. It's absolutely worth it. Moving on. This means that beyond the melting point and the freezing point, we have a third point to consider, the supercooling point. This is the point where the liquid, in this case the spider's hemolymph, is forced to change from its supercooled liquid state into a solid state. When Dumas did his experiments, he determined the freezing point by lowering the temperature of the hemolymph while introducing an ice crystal, which is why the hemolymph froze at just a few degrees below zero. When he cooled live spiders, they had no ice crystals in them to begin with, and the proteins and the glycerol in the spiders' bodies prevented the formation of ice crystals, allowing them to supercool all the way down to minus 26 degrees. However, it was only the spiders he collected in February that could survive at temperatures that low. When he collected the same kinds of spiders from the same place in June, he found that they froze solid at only minus 6 degrees. So the supercooling point of spiders changes throughout the year, and the spiders produce these proteins and other substances, called cryoprotectants, in response to falling temperatures and shorter days. In 1996, Koichi Tanaka at Hokkaido University compared the summer and winter supercooling points of the common house spider, Peristeatota tepidoriorum, from different locations in Japan. During the summer, all of the spiders had roughly the same supercooling point, around minus 8 degrees. But during the winter, while the spiders from Naha in the south, where the temperature never dropped below about 7 degrees, showed basically no change in their supercooling points, the spiders from Sapporo in the north, where the temperature could reach minus 20, had altered their supercooling points all the way down to minus 20.6. A couple of years earlier, Tanaka had also found that the spider's ability to supercool was limited by ice nucleators in the gut, meaning that in order to enhance supercooling, the spiders needed to stop eating. And that's exactly what he observed. The Naha spiders continued to feed throughout the winter, while the Sapporo spiders didn't eat at all. Many spiders lay their eggs in the fall, and the eggs don't hatch until the spring. In those cases, the eggs themselves have a supercooling point low enough to prevent freezing through the winter. Interestingly, supercooling isn't just a way for spiders to not die while they're in that unresponsive chill coma state. There are some spiders, like Bolophyphantes index in northern Europe, that make webs on snow and capture and eat prey, all while in a supercooled state. It's super cool. That's for my kids who have finally learned to appreciate a dad joke. So, supercooling is a critical ability that allows spiders to survive through the winter, either as eggs or as juveniles, and sometimes even as adults. It's easy to fall into out of sight, out of mind thinking when winter arrives and we don't see spiders very much anymore. But they don't just stop existing. They carry on from year to year, down in the leaf litter, under bark on trees, on the sides of buildings, sometimes as eggs in an egg sac and sometimes as juveniles or adults, and some of them are more active than we might imagine during that time, which is surprising as winter conditions may, to our eyes, look unsurvivable for such small and fragile creatures. But there's a genius in nature beyond anything we could devise or imagine that gives even its smallest beings a means to carry on. If you found this video helpful, give it a like. It goes a long way. And subscribe for more spider content. Check out the Shopify store for some channel merch. Get yourself a mug and put something hot in it because it's winter and most of you aren't cold-blooded. And if you want to support this channel, Patreon is the very best way to do it. There's behind-the-scenes stuff and stories from everyday spider interactions I have, additional research notes that don't make it into the videos, and I greatly appreciate the support of all of my patrons. Thank you very much for your support. It's what makes this channel possible. Of course, just watching this video supports the channel, so to all of you, thank you so much for watching. I hope you've learned something about how spiders survive the winter, and I hope to see you next time. Cheers. Some kind of impurity in the water or a rough surface in the container for water molecules